Have you ever wondered what makes an electronic circuit reliably deliver power, day in and day out, without overheating or failing unexpectedly? The answer often lies in components you might overlook, like diodes in a rectifier. Yes, absolutely, load current profoundly influences diode selection in rectifiers. It is one of the most critical factors determining the suitability and reliability of the chosen diode for any given power conversion application. Ignoring it can lead to inefficient operation or even catastrophic component failure. The primary reason lies in how diodes operate under electrical stress. When current flows through a diode in the forward direction, there is an inherent voltage drop across it, known as the forward voltage. This forward voltage multiplied by the forward current results in power dissipation within the diode. This dissipated power manifests as heat. The greater the load current, the greater the forward current through the diode, and consequently, the more heat generated. Every diode has a maximum average forward current rating, often abbreviated as IFAV, which specifies the maximum continuous current it can safely conduct without exceeding its thermal limits. If the actual load current regularly exceeds this rating, the diode will overheat. Prolonged overheating accelerates degradation and can lead to a condition called thermal runaway, where increasing temperature causes more current to flow, which generates even more heat, eventually destroying the device. Furthermore, the type of rectifier circuit, whether it is a half-wave, full-wave center tapped, or full-wave bridge rectifier, also influences the current seen by each individual diode. For instance, in a full-wave bridge rectifier, the total load current is shared between two diodes at any given time, meaning each diode carries approximately half of the total DC load current. In a half-wave rectifier, a single diode carries the entire load current during its conduction phase. Understanding this current distribution is vital for proper IFSM selection. Additionally, the rectifier circuit will experience peak currents during the charging of filter capacitors. This inrush current, known as the forward surge current, or IFSM, also needs careful consideration, as it can be significantly higher than the average load current for short durations. So, how do you incorporate this into your design process? First, accurately calculate the maximum average DC load current your rectifier circuit needs to supply. Then, identify the peak repetitive reverse voltage, or PIV, that the diode will experience. After determining these fundamental requirements, you select a diode whose IFSM rating is comfortably higher than your calculated maximum average forward current, and whose PIV rating exceeds your maximum reverse voltage with a sufficient safety margin. A common practice is to apply a derating factor, ensuring the chosen diode can handle at least 125% to 150% of the expected maximum average forward current, accounting for variations and environmental conditions. Beyond the average forward current, understanding a diode's thermal resistance, often denoted as R subscript TH, provides deeper insight. Thermal resistance indicates how effectively the diode can transfer heat from its junction to the ambient environment or to a heat sink. A lower thermal resistance means better heat dissipation capability, allowing the diode to handle higher currents for a given temperature rise. Different types of diodes, such as standard recovery, fast recovery, or Schottky diodes, also exhibit different forward voltage drops. Schottky diodes, for example, have a lower forward voltage drop, meaning they dissipate less power as heat for the same amount of current compared to standard silicon diodes. This makes them highly efficient for low voltage, high current rectification, where minimizing power loss is critical. Considering these subtle but significant characteristics can elevate your designs from merely functional to truly robust and efficient. Ultimately, the meticulous consideration of load current, its direct impact on heat generation, and its relationship to key diode parameters like average forward current and thermal resistance is paramount for successful rectifier design. By carefully selecting diodes that can comfortably handle the expected current demands and effectively manage thermal stress, you ensure the longevity, efficiency, and stable performance of your power conversion circuits, moving beyond simple functionality to truly reliable engineering.